Hello, everyone. Thanks again for attending my lecture. This short recording is to go through the solutions of homework number 1. So this homework was essentially dealing with the same example that I presented in the lecture on the transistor level design of a bootstrap circuit. And what we did in this lecture example is blatantly ignore any top plate parasitic that this bootstrap capacitor may have. Now, it depends a lot on what technology you have, but oftentimes there's a significant percentage of this capacitor will be seen as a parasitic to ground. If you have a very nice MIM cap, maybe this is just 1%, but if you use metal capacitors, often this can be 10% or more. So in this example, we're just looking at that case with an example of 10% of stray capacitance here to ground. And now resize the circuit, find a new value of the bootstrap cap and the widths to achieve the same specs that we attained in the lecture example. So this is expressed here. Find the new initial design values for CB and W of the main sampling switch. I say initial because, as you know, in the design process, we took several steps and actually gradually increased the size of CB. So this is just for the first simulation. And here are these conditions again. We want to have a ratio of 15 between the bootstrap cap and the large signal capacitance of the main switch. And then we want to have the same budget allocation of small signal capacitance to CB. But now we assume that this is pretty much taken away by this capacitance. This is all allocated by this capacitance because it's very large. All right, so here is now the solution to this problem. So we have our starting point, as in the original example, with estimating the gate overdrive voltage. And so this is the formula from the lecture notes. And so the new thing now is that we have this 10% of parasitic here included in red, and that gives us a overdrive voltage of 0.13. It was a little bit larger in the original example. Now we proceed and we use the distortion equation to get a new estimate now of what will be required for the switch bandwidth. So we have here the different components. In red, the gate overdrive voltage is different from the design example. And then here our budget for the small signal capacitance is eaten up by the top plate parasitic. And this is just the overall budget from the distortion spec that we have. So we can solve this for the corner frequency of the sampling switch and the sampling cap. That's now 9.9 gigahertz. And from here, we have the bandwidth and we have the capacitance, so we can calculate the resistance. That gives us a W over L ratio, a width. And then once we have this width, we actually know how much large signal capacitance there is from the transistor, and we have the ratio to the bootstrap cap. And so we end up with 1.8 picofarads. So what's highlighted in yellow here is what I asked you to solve for. So you see the outcome is somewhat logical. We have more parasitics on the top plate of the bootstrap cap. So we pay this with a larger bootstrap cap and a larger switch to get the same specifications in large bandwidth and so on. That lead to the improved or the rejection of this additional parasitic. So this is basically it, but I want to show you something else that's interesting if you have some more time. I actually gave the same assignment to my friend Claude, and here you can see my prompt. I told it I have attached 2 files. The first is a lecture explaining how to design bootstrap sampling circuits. The second is a homework assignment, solve this homework assignment. And to my surprise, it did it very well. In fact, it did it a little bit better than I did, because it ended up using the exact equation for VOV. I approximated this with a first order approximation, but Claude ended up using the exact expression. It therefore got a slightly different value of VOV, and that ripples through. So the bandwidth is a little bit smaller, 8.9 gigahertz, and therefore the switch is a little bit smaller. 47 microns, and the bootstrap strap cap is a little bit smaller. But interestingly, all of these steps are totally correct. It just decided to use less of an approximation that I did. And in the end, it provides a very nice summary table on the original design and the widths and the CB. So I should have done the same thing in my solution. This is actually slightly better than what I provided. Okay, with that, give it a try and see if AI also does it as well as it did here for you. And perhaps you can continue to use AI for similar problems. So thanks for listening.